Hello, so in this video we will talk about generating functions and how they can be used to solve different kind of problems. So a generating function of a sequence, so the definition goes like this. So if we have a sequence A0, A1 and AK to this, so the generating function of this guy is given by g of x. This is equal to um, k is equal to 0 to infinity ak x to the k. Okay, so if we have, for example, if we have a sequence like this 1 1 1 1, then our genetic sequence is just a0 plus a1x plus a2x squared plus a3x cubed, and since all of them are 1, so this is equal to uh, this is equal to 1 plus x squared plus x cubed. Okay, so let's see some examples here. Okay, so let's say we have ak, this is equal to n choose k. So this means that our g of x will be equal to k is equal to 0 to, and we also have for k less than equal to n. So k is equal to 0 to n choose k, x to the k. So here I can say, so this is equal to k is equal to 0 to n choose k, xn, 1 to the power of n minus k. So this is equal to 1 plus x to the n because of binomial theorem. Okay. Okay. Let's see another example. So another example is if we have ak is equal to some alpha to the power of k, then this means our sequence goes like this: 1 alpha, alpha squared, and so on. So our g of x, this is equal to k is equal to 0 to infinity alpha to the k, x to the k. So I can write here, this is equal to k is equal to 0 to infinity alpha x to the k. We know that this is a geometric series here, so here we can say 1 minus alpha x. So now note that a geometric series for this one is only defined for x a alpha x less than 1, but we don't care here. We don't care because our x's are just the uh, placeholders here for the coefficients, so a convergence is not an issue here. So whenever we have 1 over 1 minus alpha x, this is equivalent to our ak is equal to alpha to the k here. Okay, now let's see some applications here. So namely, we have, I'm going to consider two kind of applications here. One is to solve counting problems, and the other is solving recurrence relations. So let's see if we can use our generating functions to solve some counting problems. So let's say we have a problem like this. We have to put 15 objects in 6 boxes such that each box has a minimum of 1 object and a maximum of 3 objects. So minimum of 1 and maximum of 3, and we have 6 boxes. So what do we want? So basically, in terms of generating functions, we will write that we have to find the coefficient of x to the 15 in the expansion of x plus x squared plus x cube to the 6. Now why do I say x plus x squared plus x cube? Because the minimum power of x I want to be 1, because minimum of 1 objects are there, and maximum power I want it to be 3. So because of the maximum of 3 objects, and 2 objects are also allowed. So whatever is allowed, I will write it like this. And we have how many boxes? 6 boxes, 6 here. So whatever the coefficient of x to the 15 is in this expansion is my answer. So now it's a matter of just normal algebra. What I will do is I will say x to the 6, 1 x plus x squared to the 6. So now my job is to find the coefficient of x to the 9, because x to the 6 is already taken care of. So 15 minus 6, which is 9. Okay, so then how many ways can I get 9? Okay, I can get 9 like this. I can have x squared, x squared, x squared, x squared, x and 1. Okay, so how many ways are there? We have 6 factorial, total number of items. First group is 4 factorial, which is x squared. One second group is 1 factorial, and which is x, and third group is 1 factorial, which is 1. So this guy is equal to 30. Then I can have another combination. I can have x squared, x squared, x squared, x. So this guy has 6 factorial, 3 factorial, and 3 factorial, which is equal to 20. Now it is easy to see that there's no other combination I can get x to the 9 here. Either I will have 4 2's, 4x squared and 1x and 1, or I will have 3x squareds and 3 x's. Okay, so now this means the coefficient of x to the 15 is 50. So this means there are 50 ways to achieve the goal. And goal is what? This is not factorial, this is an exclamation mark. So the goal is putting 15 objects in 6 boxes such that this is okay. So the problem is how many ways? Okay, so this is the first application of generating function. I think this is an easier way to do that. I mean, the other way is obviously to count properly, that if we have one here, one in the first one, two in the second one, two in the third one, and so on. This is also possible. Actually what we are doing is exactly the same, but when we see polynomials, then it's easier to do because it comes naturally to us. Okay, so let's see now another example of generating functions, which is the other example is the recurrence relations. So now let's say we have a question like this. What we want to do is we have ak, this is equal to 5 ak minus 1 minus 6 ak minus 2, and the initial conditions are a0 is equal to 6 and a1 this is equal to 30. Okay, now let's say our generating function is ak is equal to gx, which is equal to not ak is equal to, the generating function of this guy is equal to, so k is equal to 0 to infinity ak x to the k. Okay, now what I can do is I can say x times gx is equal to k is equal to 0 to infinity ak xk plus 1. Now I can play with the index here and write it as k is equal to 1 to infinity a k minus 1 x to the k. So this is equal to um, a0 x plus k is equal to 1 to infinity a k x k plus 1. So then I can write it as a0 is what? 6x plus, and then I can start the summation from 2. So then a is equal to 2 to infinity a k minus 1 x to the k. Now note that this g of x, this also I can write it as a0 plus a1x plus k is equal to 2 to infinity ak xk, which is equal to 6 plus 30x plus k is equal to 2 to infinity ak xk. Okay, now what is, let's say we have x squared gx. So this is equal to k is equal to 0 to infinity ak x k plus 2. So this is straightforward. We can say k is equal to 2 to infinity a k minus 2 xk. Now note that why is this summation equal to this? Just a recap on how to change index from the summations. We have k a0 first. So here also a0 first. Then we have x squared first, and here also because k starts on 2, so x squared first. So whenever you change the index of a summation, just always check a few terms whether if you put k is equal to this here, what you get for the other term for k. So if I put k is equal to 5 here, for example, so I get a5 x7, and then if I put k is equal to 7 here, I get a7, a5 and x7. So a5 is associated with the x7 here, and a5 is associated with x7 here. So this means that this is correct here. Okay, now what do? We make use of this guy. So then what I'm going to do is I'm going to do gx minus 5x gx plus 6x squared gx. This is equal to what? So gx is what? 6 plus 30 plus k is equal to 2 to infinity ak x to the k minus 5 times, and 5 times this guy. So I will say 5 times 6x plus k is equal to 2 to infinity ak minus 1 xk, and then plus 6x squared gx. So x squared gx is this guy. I'll say plus 6 k is equal to 2 to infinity ak minus 2 x to the k. Okay, now this 30 goes with this 30x. This is this 30x, this goes with this 30x. Okay, so then I will get 6 plus k is equal to 2 to infinity ak minus 5ak minus 1 plus 6ak minus 2 times x to the k. Now what is this guy? Since ak is equal to 5k minus 6ak minus 2, this guy is 0. So my answer is 6 here. So this means that if I take gx common here, gx 1 minus 5x plus 6x squared, this is equal to 6. So this means that gx, this is equal to 6 over 1 minus 5x plus 6x squared. Now I can factorize the denominator. So this is equal to 6 over 1 minus 3x, 1 minus 2x. If you use partial fractions to simplify this, what do we get? We get 18 over 1 minus 3x minus 12 over 1 minus 2x here. Okay, now what does this represent? Okay, so this I can write it as 18 times 1 over 1 minus 3x. So what did we say? This guy represents, if we have 1 minus alpha x, 1 minus alpha x, this represents alpha to the k, right? So then this means that this is represented by 18 times 3 to the k. And the next guy, obviously we have 12 over 1 minus 2x. So this is represented by 12 times 2 to the k. So this means that my ak, this is equal to 18 times 3 to the k minus 12 times 2 to the k. Okay, so this is how to solve a recurrence relation using generating functions. So I wouldn't argue with this method or using the characteristic equation to solve a recurrence relation. Sometimes if it is non-homogeneous, in my experience, this method is harder. But I think sometimes when it is the initial conditions are such that we can cancel out some terms. Remember that 30x was cancelled with 5 times 6x, so it made our life a little bit easy. So in my experience, I mean, it's hard to say which one is better, but it's good to master both methods to solve recurrence relations. But this generating functions are definitely a good good method to know, to apply if possible for different kinds of recurrence relations and different kinds of counting problems. So sometimes this is also known as ordinary generating functions, because then we have, in probability we have moment generating functions and stuff like that. So just to separate them from those kind of generating functions, they are known as ordinary generating functions. So this is it about generating functions. I hope it was easy to understand. Thanks for watching and hope you like the video.